So very good morning to you all. We are having our second session of SPSS workshop. As I discussed with you that this session is mainly from the practitioner's point of view. I will tell you the conceptual things as and when applicable, required. But this is not an econometrics course, so I don't want to go too much into the conceptual things. But if you have any questions, of course, you will get the answers. Now, this is the same data which we transferred from Excel to SPSS workspace. And if you remember the Excel spreadsheet, which you can find in the Moodle workspace, I colored the variables. So for example, there was some common color of accounting variables. Then there was some common color of stock market variables. And similarly, the corporate governance variables were colored separately. And I think there was one or two growth variables, the growth-based variables. All right. So we had some categories of variables. So we grouped them. Remember that today, at some stage, I would call them the groups of variables as factors. So I can say accounting factors. So that would mean all the accounting variables. Then I can say the stock market variables. That means it's a collection of all the stock market variables into a factor. But without going too much into details yet, I want to take you to the variable view. And you can see that they are the same variables. So you can see that there is a free cash flow, total revenue, log of revenue, operating profit, return on capital employed. So if you see variable 1 to 5, they look like one common feature of variable 1 to 5 is that they are accounting variables. And then the stock market return, the FTSE return, all that, market cap, log of market cap, they are represent, and even the price to earning ratio, they all look like the stock market variables together as a, so I can say all variables in stock market factor. And then the median board size, education, experience, they are showing the board of directors characteristics. So I can call them as a corporate governance variables. And then we have one innovativeness as a variable, which shows the company's growth perspective. So if I have to split, if I have to categorize these 19 variables into factors, there are 4 factors. There are accounting factors from here to here. Then there are stock market factor. Then there are corporate governance factor. And then there is a one variable, one factor. So that's a growth factor. All right. So we can put them into some categories. But it's just for your, at this stage, I only want you to remember that these variables can easily fit into factors. Okay. And how do you categorize them? How do you know that they're falling in these factors? Well, it depends on your knowledge about the theory. And where do you study the theory? You study theory in the review chapter, literature review. And when you know that these are the types of variables, this is their impact, this is how they move. So all these things you study in your literature review. So unless your literature review is ready, sorry, you may find it a bit hard to run the analysis test. Okay, so we move on. And today we move on to regression, from correlation to regression. The only thing which I can say about the regression is that last week when you studied correlation, we were focusing the key word called association between variables, but we were not studying cause and effect relationship. We were studying that there may be some association between, if I give you non-financial example, there can be some association between education level and the crime rate. But I didn't say that crime rate have an impact on education or whether education have an impact on the crime rate. So we were not studying the cause and effect kind of phenomenon. In regression, we study the cause and effect type of phenomenon. And if I can quickly give you a bit of theory of regression, because I said that you get some information when you join me today. If I have to say something about regression, the theory of regression, I would say that in the most of you will be applying multivariate ordinary least square regression method. Why we call it multivariate? Because there are many variables. Why it's called ordinary least square? Because this is the purest form of regression. So the base regression you'll be using. And what happens in regression? In regression, we have a dependent variable y. It's called dependent. It's also called explained. And it's also called predicted variable. So different names, but I think most often I use the phrase dependent, predicted variable. And then we have many x variables, like it could be x1, it can be x2, and up to xn. But the thing you need to remember is that they are, in theory, they are always represented as the capital letter X. So we say X's affect Y. And these are called, by the way, if you see the first dependent, so they would be independent. If the top one is explained, then they are explanatory. And if top one is predicted, then this would be predicting variables. And if you have to make a formulation, a mathematical formulation, then it will be called that y is a function of x1, x2, x3, and it can be xn. Some of my students have done regression and they have taken over 10 independent variables. It's possible. So this is a simple looking thing. This is a simple looking regression model. Okay. Any questions so far? So I can say, if I give you an example that, let me give you an example that if y is a welfare, remember that we discussed last week that if you want to measure the welfare level in uvascula, you can measure, that's a phenomenon variable, but you can measure this phenomenon of welfare in many ways. So maybe you want to say that the crime rate, okay? So if the crime rate is less, that's a symbol of increased welfare of people. So let's say crime rate depends on, Well, it depends on many factors. It depends on maybe your X1 is the age factor. We assume that the younger people, I mean, please don't misjudge me. I'm just creating some hypothetical theories. Let's say you have studied the literature and you find that the most of the criminal habits are, the acts are generally committed by relatively younger people. Let's say for the sake of, so it means your X variable, X1 variable would be the age of accused. So it means you have a data, one column of crime rate, and then the second, you have the variable age of accused. The second variable, perhaps you can see that if people are more educated, if the education level is high, they resort to lesser criminal activities. So then I would say the education of accused. One more variable can be that if parents are more educated, then the kids are less likely to commit silly things. So it can be also a new variable, education of parents. So X3 can be education of parents. If in a city, if the local council is providing lots of healthy activities like gyms, you know, these what is it called them, gymnasiums, or these kind of sports complex, or some cultural events, auditoriums. So if the local council is providing lots of you know, the sports and cultural things, then also people are less likely to commit you know, these crimes, because their energy is channelized. If people are relatively having high living standards, then I would say that the kids are less likely to do something silly. So can you see here, I'm making, so all these variables, all these independent variables on the right hand side, they can have an impact on the dependent variable in this example. Yeah. So can I say that crime rate is predicted by multi-variables? If there is only one variable, only one, let's say only age of accused, then this is called simple linear regression model, or simple linear ordinary least square method. But if you have more than one, then the name is self-explanatory. If it is more than one, then it's multivariate. In this case, there are 1, 2, 3, 4, or 5 maybe. So you can have host of variables. There is no limit to it. But we can't have indefinite number of independent variables, because then you have to have more data also. Okay. All right. So this is the little bit of theory, and each. I hope you remember this picture, that we take the dependent variable y-axis and the independent variable x-axis. Yeah. And if you plot them, like for example, let's say that the y is a crime rate and x is x1. And let's say we find x1, the age of accused. So we find that this type of relationship is formed. We plot them. Yeah. It means more is the age of accused. No, did I say opposite? Because in theory I said that opposite here. Okay, let's see that we have this type of relationship. No problem. Which basically means that as the accused become older, the age goes up, people tend to become more peaceful, they become more law-abiding. I mean, just a theory, just some kind of. And these kind of relationship, these kind of theories, you understand in literature review. Sometimes these theories are well established, and sometimes you make your own arguments. Okay, and how do you measure this change? Can you see that in, let's say this kind of slope is in uvascular, but when you have the same research in Helsinki, then you have this type of slope. Both are downward sloping curves. The theory and the actual life are matching, but still I would say that the lines are not same. So you can say that here the slope is sharp and here the slope is small. Do you know the meaning of slope? Slope of a straight line? You can walk on the floor here in the floor, yeah, right? Why can you walk so easily? Because there is zero slope. Yeah, there is zero slope. But can you walk like this? No, because the slope is infinity. And as the slope is between 0 and infinity, as the slope goes up, you find more hard to walk. So that shows that what is the trajectory of the relationship. So beta, the B is the slope. Each variable, age of accused, education of accused, education of parents, sports cultural, living standards, they all will give you a slope. And that slope is called regression coefficient. That slope is called regression coefficient. Then we will decide by using the test of significance whether this relationship is significant or not. Remember last week we studied correlation? And we studied correlation by checking the test of significance. And we put a line that if the significance level is 10% or below, which means the level of confidence is 90% or above, we accept a phenomenon. But if the level of significance is more than 10%, then definitely your level of confidence would be below 90%. And then you say, no, this relationship is unacceptable. You with me? Yeah. So the same argument, the same logic would be applicable here. Now, since I told you last week that you guys should have a look at some basic fundamentals of regression. Is it so that you have studied something about regression, which I haven't covered in my lecture so far? Or is it so that you did something, you studied something, but you didn't understand, and you want to take my take on that? Is it so? Do you have any question about regression? Are you fine? So while you're thinking, I can give you a quick recap that the correlation and regression are like first cousins. And the difference is that in correlation, we only study their association. I can say that age of accused and crime rate are associated. There is some association between them. But I would never say in correlation that is the age causing the crime rate, or is it the, of course, crime rate can't cause the age. But sometimes it happened that, for example, let me give you some other example. Sales and advertisements are correlated in a company. Then the question is that is the amount of advertisement have an impact on sales revenue, or is it the sales revenue determine how much you spend on advertisement? How is it possible that your revenue is going down and you're still spending on advertisement? And then how is it possible that you are spending on advertisement, but there's no impact on the revenue? So that way, the correlation is somewhat cyclical. You never know who causes who. But in regression, we are very specific. very specific. And why you become so specific? Because you have studied lit review. And you know that to the best of your knowledge, based on the studies you have reviewed, you can say that this variable causes that variable. So you know where is the arrowhead and where is the arrow tail. Yeah, that is the regression. When you know that this causes that. So there's a cause and effect relationship. So I can see that all these variables here, age of accused and so on and so forth, they all are cause variables. And the crime rate is the effect variable, combined effect of several variables into one. When you do this kind of thing, it's called regression. If it is one-to-one, one independent, one dependent, well, dependent will always be one, that's for sure. But independence can be several. If independent is one, then we simply call it simple linear regression or simple OLS, ordinary least square. By the way, you will often see this phrase, OLS, because that's very well accepted abbreviation for ordinary least square. Yeah, so you want to see that how these variables independently and together, look, independently and together, or in the groups, have an impact on crime rate. So this is the theory of regression. But if you have any point to ask me or point to share with me, please feel free. Is anything you want to discuss? So now we are into, after explaining the theory of regression, now we can actually go to our SPSS analysis. And as you can see that we have the variables, the same variables which we discussed last week. And let's say that we want to analyze now. Now you have to go slow and very, very careful. I told you last week that most of your operations will be coming from here, analyze. So if you click analyze, see the regression. Can you see it? I go slow, analyze, regression, and then linear regression. So I stop here for a second. Analyze, regression, linear. Why linear? Remember the phrase, ordinary least square. So that shows the linearity, linear regression. And remember that when I drew this picture, this strange looking picture, x-axis and y-axis, the line which I drew downward was almost a straight line. So it's a linear regression. So we assume that the relationship between the variable is linear, which is an assumption, and which can be horribly wrong, but that is also theory. Yeah. So I repeat, analyze, regression, linear. There we go. When you click this, you have this dugout. Remember the word dugout? Dugout is that where our variables are resting. And now we need to bring them to the activity level, activity area. And this is the activity area. But here, you see, there is a, by default, categorization of dependent and independence. Look, even SPSS knows that the dependent can only be one, but independent can be one or many. That's why this is independent bracket S. So they can be independent. And I hope you remember that we want to find out our, let's say our dependent variable is annualized firm stock return. So in this model, in this example, we want to find out which factors affect our annualized firm stock return. So basically you are studying in this example on what factors, on what variables the company's stock return depend on. So you want to find the causes of the movement in the stock prices, in the stock return. Daniel, it's okay? And then we find out that I'm not including free cash flow. I'm not including total revenue. And I'll let you know why I'm not including them. Okay. I take the natural logarithmic value of total revenue. Yeah. Then I add operating profit. And where I'm adding them? In the activity field of independent variable. So here I'm saying that total revenue, when it's shown in the logarithmic form, have an impact on the stock return, operating profit return of the company, have an impact on the annualized return. And then I have the annualized FTSE 100 return. So it means that in this example, I'm taking the British companies. Yeah. And what index we use in UK for the top companies? Financial Times Stock Exchange 100, FTSE 100 companies. And then I take market cap. No, I don't take market cap. And I will let you know why I'm not taking market cap. Instead, I take log of market cap. I take log of market cap. And then I take price to earning ratio, median. Actually, then onwards, I take all of them. And if I press shift, I can add all the variables together if they are all going to be same. So I repeat, if I press shift and use the arrow, down arrow, I can select them and I can put them together. So now you can see that my theory says that all these variables have an impact on the firm stock return. Question: why didn't I include free cash flow? Why didn't I include total revenue? Why didn't I include market capitalization? Market cap means the market value of the company. I chose not to include that. The reason is that if I include the absolute values as such, then I'm adding by choice a problem of size effect. Then obviously bigger firm, my result would be biased in favor of bigger companies. You with me? So therefore, when you do the SPSS regression analysis, make sure that try to neutralize the size effect of variables. Either take the ratios or logarithmic values. So for example, or instead of log of total revenue, I could have taken total revenue to assets ratio. Perfectly fine. Or if I don't find a ratio, I can include the logarithmic values, because logarithm reduces the size quite significantly. You know how to change the logarithmic form? In Excel, it's very easy. You just need to take ln equal to and then select the data. It will give you logarithmic values. So do you know the reason why I'm not taking some variables? Because some variables, look, if I have a sample and in that sample, I have British Petroleum, Finnair, all the multinational companies, many multinational companies. Then I also take some small startups. And I'm including their actual revenue or actual assets or actual market value as such as a variable, then I would be accused of manipulating my results in favor of the big companies, because the big company have more impact because they have a big size of values. So the result would be twisted. So to make them, to bring down the size effect, we can use the ratio or logarithmic or non-linear, but I will not go too much into that. Look, I chose to have log of revenue, but not the total revenue as such. In the market cap, I chose to have the logarithmic value of market cap, but not the actual market cap values. So now you know why I chose not to take some variables. Is it okay or not okay? Okay. Please feel free to ask me. And then when we're done with this, we go to statistics here. Please go slow and together. We go to statistics.
Can you show all the independent variables that we are taking?
You mean in the Excel or in the?
What are all the independent variables?
Bigger the window so we can read the name of the.
These ones, yeah? Yeah, it's possible. So these are all the variables. You can see here natural log of total revenue and operating profit ratio. Annualized FTSE 100 return is your dependent variable. And then we have log of market cap, price to earning ratio of the company. Yeah, price to earning ratio of the company, and then the median board size, median education experience, debt to equity ratio, and innovativeness. So I took all the variables which are not absolute values, which are relative values. Yes.
What is that like? I just whatever valuation represents.
Yeah, I can explain it to you. Good that you asked me. I keep it here. Let me create an example for you. No problem. This will be clear as well. Just bear with me. Why is taking so much time? Okay, here we go. Okay, please have a look at this. Imagine our variable is firm assets. And let's say we have 10 companies here, firm A, B, C, D, E, F, G, H, I, J, K, and L, imagine. And firm A, total assets are 3,000 euros. Firm B's assets are 15 million. Firm C's asset, Firm C is just newborn company and it just started maybe yesterday, maybe 250. Only asset they have is a laptop, cheap laptop. Some company has 1,000 assets. Some companies is also multinational and it's about 34 million. 1, 2, 3, 4, 5, 6. F in between somewhere. G is also a very big company, some 12 million. 2, 3, 4, 5, 6. 27. Can you see this type of data? If you look at this data, the size effect is very, very visible. It means that when I make any calculation based on these actual numbers, actual figure, the result would be a bit twisted and unreliable because the data differ from 3 digits to 8 digits. You know, massive difference. But when I put them, if I take logarithmic log values, log assets, let's say, see what happens. Natural log, see what? It's something 8 point. I can actually format it to 2 decimal places, maybe. Number 3 decimal places, maybe max. Look, the numbers look so well behaved, isn't it? Something is in million, and that is also 17 point something. Now look the difference between the smallest and the largest number. Is the difference, is the size effect neutralized? Can you see that? By the way, can you see this in Zoom? Can you guys see this example or not? Student who are in Zoom, can you see the, because I don't know if I share it.
Yes.
Okay, good. So see that something worth 250 million is 5 point something, and something worth 15 million is about 16 point something. So look at the difference. The gap between small and the range of the gap between small and big number is now reduced. Just minus 72 million and 234, there's hardly anything you minus. But when you minus 17 point something and minus 8 something, it's quite visible. It makes a big difference. So to neutralize, to nullify, to take away, to discount the size effect, we sometimes transform the actual numbers to logarithmic numbers. And it's very simple. All you need to do is use the natural log function in Excel and pick up the data, and there you go.
Do you have like some average?
Sorry?
Do you have some average?
Where is the average? I didn't talk about average yet. We are only taking the data. What I'm saying is that you can transform the actual data to logarithmic data. And by transforming to the logarithmic data, you make data free from unnecessary, very big and very small values. So the range of values becomes small, the gap between the maximum and the minimum. Standardized, yeah. So we have actually, Fernanda used a nice phrase. So we have more standardized comparable data. How can you compare 234 and 72 million? Now you can compare 5.521 and 18.092. Look, they look more comparable now. Look at that. Compare this with this. It's absolutely bizarre comparison. But now compare this and with this. It looks more reasonable, isn't it? So we have made our data more reasonable, basically.
But for example, if we will multiply, for example, C variable, for example, 541 multiplied by 3, we wouldn't get the same number as we multiplied 353. But I mean, if we will multiply less logarithmic variable, we will get like more.
So what do you want me to multiply, and why? Why should I multiply something? These are the actual observed data. Why should I multiply 250? If companies sees assets are 250, then they're 250. Do you understand this example even? We took 10 companies from A, these are their name, and we want to see how much assets they have, property they have. And this company have only 250 euros assets. Actually, these are observed values, observed real values. So we imagine that they are the real values, took from the balance sheet or wherever. And these are the transformed. The problem with this thing was that the range of values too big. Compare 72 million with 250. Doesn't make any sense. But when you transform them to the logarithmic values, then the range, the gap becomes small. That's my idea, but do you get it actually or not?
Yeah.
So by transforming the range and the size impact. Now this is 18.092. It's not 18 million now, even though it belongs to 72 million. So this number, very big number, doesn't look too big, and very small number doesn't look too small. That's what we want. A very big number is now looking smaller, and very small number is looking now a little bit bigger in terms of comparison. That's what we have done. So that's why if you take the absolute values, these are the absolute values, it can cause a problem in the analysis.
Natural logarithm of total revenues are like the natural logarithms of total revenues that we have here.
Yeah, so we had actually when we collected the data, it was the companies never published logarithmic values in their annual reports. They published the actual data. But after we collect it, then we transform it. And how we transform it? The way we transform here. Just put logarithmic and everything. It's easier, and not only easier, but also make our results more defensible. We can defend them. Otherwise, the first question you'll be posed by the teachers, and if you publish it as an article by the publisher, what is this? You are taking thin air in your sample, but you also have a small startup somewhere in Uvascular.
Only compare thin air with the air scale.
Yeah, but that's still a okay type of comparison. It's not that. Yeah, but if you take some random sample, any company has a chance of being selected. Then the range, the extremity of difference between the values can be too big, and that it's like comparing apples with banana. So you want, when you make them logarithmic, then they become a little bit more better than before. I'm not saying the best comparison, but at least they look better than before. Look, the range between 18 and 5 is tolerable, but the range between 72 million and 250 is intolerable. That's what we want, that we make number more digestible in our head. Okay, you fine with this now, or you have a question?
Just one more question. Can we apply some logarithms?
Huh?
Can we turn variable of logarithms back to the number?
Yeah. I think if you go and you do anti-log, maybe. If you take the, what is the, how do you say anti-log? I have to check.
Well, in mathematics here is a specific formula for that, whatever. It's like maybe a log.
Inverse logarithmic. Okay. Inverse logarithmic. So let me try if I can do inverse logarithmic. Inverse log. What is the symbol? That I don't know. I have to check the symbol. You are asking me very questions which are. No. I want to be sure of myself before I do something. To normal values. So there was one question that if we have the original value and then we have the natural log value, and how can we bring them back? If you want to bring the numbers back, then use the exponential function. So exponent of the selected value, and then that will give you the original values. Okay, so let's go back to the workspace, SPSS workspace. Let me know if you can't see it. So now with the variables are selected and we know in which form the variables are selected. I have not taken free cash flow because I didn't have the because that is also the absolute value. But if I create one more column in Excel, or even in fact, you can transform the variables even in SPSS. You don't have to transform in Excel and then bring them to SPSS workspace. So for example, if I transform and compute the variable, and let's say my target value is log free cash flow, then I can say that natural log of free cash flow, and see if it works. Okay, the expression is incomplete. Okay, so I need to break it. So if I say look, now I have the automatically calculated variable log of free cash flow. Can you see it? So my variable is automatically created in the SPSS workspace. So you don't have to do all these transformation in Excel. You can even do as the need be, even in SPSS workspace. So all you need to do is just transform, compute a variable, and give the command. It works. Okay. Now I think when I go back to my analyze, regression and linear regression, because now I have the log free cash flow, then I think I need to first select all the variables first. So your dependent variable is annualized firm return. Fernanda, now see the we go step by step again. So we have the log of total revenue, we have the operating profit, we have the return on capital employed. We go there, and then we have the FTSE return annualized. We don't take market cap, but we take natural market cap. We have the price to earning ratio. And I think then now onwards, we can take all the variables and including log of free cash flow. Now it's fine. Now it's okay. Sorry. Yep. Something's wrong with my throat now. Statistics we take here. The estimates will be there, and the confidence interval by default is 95%. If your confidence interval is 95%, what is the level of significance here? How much? 5. Let's make it 90, because up to 10% confidence, up to 10% significance is okay. Okay, You fine? So if the level of confidence by default, if you see, by default, it's 95, as you can see here. But of course, you can change it to 90, but never bring it down than 90. Otherwise, your results will not be reliable. Now be careful what we need. We need descriptives, even though we don't need descriptive because we can calculate them separately. Last week, when we did the workshop, we had a separate discussion how to find the descriptive statistics, okay? I would say that take the collinearity diagnostic, descriptive, no. Then Durbin-Watson test, you should. Collinearity, Durbin-Watson, and continue here. You don't need anything else. Plots, I don't think we need anything to plot. Save. No need to save anything. Options, no. Is anything in plots, by the way, we need to take? No, there's no need. So basically, we don't need anything except that we need some statistics, and we chose estimates. They are by default. Confidence interval, you can make it to 90 instead of 95. Descriptive we do separately, and collinearity diagnostic you take, Durbin-Watson you take. I'll explain the meaning of whatever I click. I will explain when the results come, okay? And then we continue. I think now the stage is set to press OK button and see how our regression results look like. You okay with this now? Any question what to pick up? Okay, and then so basically we all the changes that we need is here. Estimates, these estimates, by the way, these are the estimates of beta, the slope of coefficients. Confidence interval, collinearity, model fit is no problem, and Durbin-Watson you should. And then if you click OK, you will see the result has shown up. And we have the first model summary. Model summary. Now, pay attention here and listen very carefully, even though you will see the video in the whenever you want, but it's a good idea that you listen here properly. And if you have a question, ask me right now. There is something called R square here. Yeah, can you see R square? R square means all the combined independent variables. Remember, we have several independent variables. Count how many. We start with the natural log of free cash flow, then natural log of revenue, then we pick up operating profit ratio, return on capital, board of directors, and so many. I would say we have more than 10 independent variables. And what are they doing? They are going to affect, these 10 cause variables are going to affect what? Our effect variable. These 10 cause variable are going to affect our independent variable, dependent variable. And who's that? Who's dependent? The annualized stock return. Is it okay? Now, all these 10 or 10 plus variables together explain 19.4% movement in our dependent variable. So if I want to draw a graph, and I want to say that we have several, we have a dependent variable and we have many independent variables, x1, x2, and up to x10, let's say. And if your R square is 0.194, it means that all these variables, independence, explain 19.4% change or movement in your dependent variable. This is a theory. So combinedly, jointly, all these independent variables put together, when they put joint pressure on your dependent variable, they are able to move it by 19.4%. And once again, unless your R square is very low, 2%, 3%, 4%, there's no reason to make any judgment based on it. So you can't say that 19.4 is too low, it has to be 100%. No, that's not possible. 19.4% is very decent impact. Very decent impact. Okay. Your R square can change. It could be, and why R square is, if you want to say, Shab, why we can push R square up? How can it go from 19.4% to 25%, 30%, 40%? I would say maybe add more variables, maybe add more data, and perhaps change the form of the variables. But none of these things you are supposed to do in this session. Okay? We don't need anything. So 19.4% R square is very good looking R square. Yeah.
Yeah, it's kind of a different number because you have calculated the free cash flow logarithm. And we have a bit different number, but here is like 13.4%.
I don't know why, because I can't say it, because I don't know how you do it. Did you take a log of cash flow?
No, we didn't take it.
You didn't take it. When you take it, it may change.
Yeah, we don't have this variable. Yeah, you just supplied an example. We didn't do. Yeah, doesn't matter.
Okay, so we go on and see the next results. So the first thing you need to look at is that your R square here. And you don't need to see R, you don't need to say adjusted R square is a conceptual thing. And if you ask me what's the difference between R square and adjusted R square, I would say that adjusted R square is more discriminatory in the sense that the SPSS pick up those variables whose individual contribution is more, and it ignores those R square of the variables whose individual R square contribution is less. So it's more filtered form, but I would say that don't worry about it. Focus on this thing. This is all you need. So in this table, in the model summary, you need basically, if I take a screenshot, because that would be good to know, snip. Yeah. Because you need to know what to study and more importantly, what not to study. That is also equally important. Why can't I have a snip? It's here, snippet. So from this table, if I need to select something, I would say select this one, and then select this one. Folks, my friends in Zoom, can you see this the screenshot which I took?
Yes, sir.
Okay, good. 19.4% is the combined movement of all the independent variables on the dependent variable. And then the next thing we need to take it is Durbin-Watson test. Durbin-Watson test, you don't need to show, you need to, maybe you don't need to understand, but there is a problem in econometrics called autocorrelation. This problem can be very severe. And the problem is with the data, actually. Okay. If your Durbin-Watson test, now I can give you legends. If your Durbin-Watson test is around 2, between 1.75 to 2.25, 0.25, you are doing great job. And the data shows that our Durbin-Watson test is 1.908. So we are safe. Okay. So if your Durbin-Watson test is between 1.75 to 2.25, it shows that there's no problem with the data. So your data is free from the problem of autocorrelation. And the autocorrelation is that when every number is correlated with the next number, that could cause unnecessary multiplications. So we have good, fair data. All right. But again, without going too much into the nitty-gritty, you need to know that if your Durbin-Watson test is between, if DW is between 1.75 and 2.25, it's fine. If it is not, then we can do something later on. But what to do, I will not tell you now. Okay, then in the next table, you look at in the ANOVA. ANOVA is called analysis of variance. And in this table, what we need to see is only one thing. And that is this, F and sig. Yeah, F and sig. How much was your R square in the previous table? Can somebody tell me?
19.4.
And what does 19.4 shows?
That independent variables can move the dependent variable
By
19.4%.
Very good. And this we can say with what level of confidence? This we can say with what level of confidence? 100%. So we can say, now listen, mark my words. Now we can say with 100% of confidence that the combined movement of all the independent variable upon the dependent variable is 19.4%. In the previous table, we knew it's 19.4%, but we were not sure if it is confident, if it is significant or not. Now it's proved that it is significant. Yeah. If I say that this coursework is fine, but by what percentage, by what level of confidence I can say that this coursework is done nicely? That we check in the level of significance. So we can say that the 19.4% combined movement, we can say with 100% confidence. Yeah. So this is a level of significance. And I would discuss last time that level of significance in a way tells the level of confidence in your statistics. Okay, we move on to the next table. This is, I would say, the most important table. And this you need to listen and understand even more carefully. So if I select them, in this table, we need to look at, first of all, this column, then these two columns. And then maybe this last one, this is because basically, yeah. What do they show? Have a look at this one. How much is the significance here? How much is the significance? Be very quick in replying. How much is the significance here? 100% what? Confidence. 0% significance and 100% confidence. And what is the value of the beta? 25. But I will not care the value of the beta. What I would care is the sign of beta. What is the sign of 25.001? Positive. Okay, and who's your dependent variable? Who's your dependent variable? I can say with 100% confidence that the log value of total revenue positively affect the stock prices, stock return. In other words, those companies which earn more also experience high stock return. And those companies whose total revenue is less, their stock return is also less. I can say with 100% confidence that I can say with 100% confidence with 0% error probability that the companies whose revenue is more have experience increase in their stock return also. So the first relationship is proved. The cause, this is a cause variable. This is the effect variable, and this is proved now. So I can say, yes, it's okay. Tick, yes, it works. Look at the next variable. Oh, it's here. What is the level of significance? Here? Where is the level of, what is the level of significance here? Convert decimal 0.6 into percentage in your mind. 6%. 6% is acceptable or unacceptable? 6% significance is acceptable or unacceptable? Because the max is 10%. It's acceptable. You can say with 94% confidence. You can say with 94% confidence that the operating return on profit positively affect the company's stock return. Why did I say positive? Because the sign of 2.614 is positive. Once again, you will not, don't go in the debate that this is 25 and this is 2. So then this variable is 12 times powerful than this. Don't go into that debate. Don't even look at their absolute, don't bother their values. Just bother, first thing, is it significant? Second, is it positive or negative? Just that's it. Make sense? Let's see this one now. Return on capital employed. How much is this? So what is the confidence?
Very less.
Very less, 32%, 36%. Absolutely unacceptable. I don't care what is the value, because this thing is, the first point of contact is this. And if the first point of contact is not good, we don't even care. What is the sign? What is the value? So I have this tick, and this cross. So we have proved that return on capital employed have no impact on the company's stock return. Look, when you prove something, it's a proof. When you disprove something, that is also proof. Are you with me? When I say that, I found that this thing impact that thing. And when I say I found that this thing doesn't impact that thing, Both are very important findings. So proving and disproving are equally important. When you prove that that guy is a criminal, let's punish him. Good job. But when you prove that that guy is not criminal, then you saved him. You served justice. Both are findings. Both are vital. So when I say that this is tick, this is tick, this is a cross, it's not junk. It's not rubbish. We proved that this does not affect the stock return. 71.9. How about this one? Huh? No. So you proved that the market index return have no impact on the individual stock return. The firm you took in your sample are totally, their stock return is not affected by, because normally, look, in theory, we believe that the changes in the market index affect the changes in the firm stock return. That's what theory says. But what we prove that it can happen, that the index values and the sample firm's value return, it doesn't go together. You know, the sign is positive. The sign is positive, but we don't have enough confidence to back up this. Market cap. Almost 100%. But look at the sign. Look at the sign. Negative. It means what? Bigger the company's market value, lower is the company's stock return. And lower is the company's market value, bigger is the company's stock return. So it means that in this sample, the small cap companies are outperforming the big cap companies. Okay, the small cap companies are outperforming the large cap companies. Some newly formed companies in the stock exchange doing marvelous job, and those old 100-year-old companies are doing comparatively bad job in the market stock return in the stock market. Yeah. Sorry. Okay. We first reach that point, and then we have this 24.1%. This is not acceptable. We don't. But what is the finding? The finding is that the price to earning ratio means if your company's stock price is expensive. And what is the sign here? Minus. But I would rather not comment anything because my first point of filtration is this. So this variable is disproved. Cross. Put a cross. Where is that? It's so minor to. Generally, we have a theory that those companies whose price to earning ratio is more, people are desperate to buy them. Yeah, higher the price to earning ratio, more is the people's attitude to buy them. But we prove it wrong. And what about the board of directors? The board size, by the way. First of all, is it acceptable? Almost. It was about to touch 10%. And what is the sign here? What do you prove then? Larger board size, the companies with big board sizes have lower stock return, and the companies with a small board size have higher stock return. It's quite understandable because if the board is very big, it's very difficult to take decisions, and that can also reflect in the stock market. But if the company's board is small, it's much easier to take decisions, and that also reflects in the stock market. How about education? Look at this first, gentlemen.
Oh yeah, here is like
yeah.
We're not confident about it.
No impact of education. no impact of experience. We believe that people, board of directors who are more educated, who are more experienced in theory, they should affect the stock market positively, but our results are not showing. Debt to equity ratio. Yeah, 1%, yeah?
Yeah.
And what's the sign?
Positive.
Positive. Debt is top, equity is the bottom. It means that the company who borrow more for the given amount of equity, they are giving splendid stock market performance. And those companies who borrow more, who borrow less, they give lower performance. And look, when you write the results in your thesis, that's not enough. You have to support your finding with the argument. The argument could be who borrow. The companies borrow more for the given amount of equity, who are very aggressive in their approach, who see that their future is so bright that the money they have in their company is not enough. They need to borrow. And when they borrow and they invest, they're very confident that the company would give good job, good return. And also, when you are a CEO of a company and you borrow more, you have more pressure to deliver the performance. But if you borrow less and all the money or maximum money is coming from equity, you as a CEO become lazy. That is called managerial slackness. Because equity, you don't have to return. Debt, you have to return. Not only debt, but you also have to give back the interest. So the managers are always on toes. They're always alert. Sorry. And if they're alert, it reflects on their performance. If you are scared of studying finance, then there's a high chance that you will take it seriously. Yeah. And if you are very confident, oh yes, it's just piece of cake, then it can backfire. So this alertness, this hard work, this keeping your mind and eyes open all the time, that results into good performance in stock market. If you work hard, if you attend lectures, if you are on Zoom, yeah, then it may be a good thing. Okay. How about the innovativeness? 100%. And what's the sign? What do you prove?
Companies which have high innovativeness,
Yeah.
lower annualized focus.
Yeah. And again, your findings are opposite to so-called theory. The theory says if you're innovative, the company's stock will go up. It's a good sign. But maybe in your case, what happened? Your shareholders are feeling that if your invention, if your innovation is unsuccessful, they would lose money. So they are scared of your innovative behavior. You see the picture? If you are very innovative, I would be scared of you because it's quite high chance that your innovation fail and I lose my money. So I don't trust too overly innovative companies. So I want that you remain peaceful and do what you're doing in the past. How about the free cash flow? Significant. And the sign is positive. The companies who have a lot of free cash flow means the final cash you have at your disposal, right? The companies who are cash rich, their companies, their stock perform better in the market. Because people know that in case of any emergency, in case your innovation fails, in case you can't pay your interest back or you can't repay your debt to the bank, don't worry, there's no panic. A lot of cash there. We can survive. So the company who are cash rich, they do splendid job. Okay. So by doing so, we are able to explain the significant variable, and we are able to filter out the non-significant or comparatively insignificant variables. Are we fine?
Yeah.
We had, don't worry about constant term. It's just like when you touch the x-axis. Constant means if a constant is positive, yeah, you see the constant is positive. If the constant is positive, it may basically mean that if you just give me a sec. If a constant is positive, it basically means that your regression line is starting from the upper side of y-axis. Yeah, so this is your constant, positive. This is origin 0. And if your constant is negative, it means that your line, your slope start from the negative level. That's the only thing. You don't worry about it. Yeah. So we don't see the constant. And by the way, your results will automatically come, and you can actually, if you click it, you can actually copy the whole table and transform to the spreadsheet or Word. It works very well. So you don't have to, yeah. So it can easily be moved to or exported to spreadsheet. Now, one thing which I haven't shared with you yet is the last thing. Sorry, what was that?
It is visible only your graph.
Okay.
This one.
Can you see this?
No.
In Zoom, you can't see this one?
No.
The VIF factor is basically this inflation factor. It also points out another problem, and try to understand that when you have big data, there can be big problems as well. Yeah. In the big data, there can be big problems. The first problem was autocorrelation. Yeah. Did you see that autocorrelation problem? And that is shown by Durbin and Watson test. And what is the benchmark? It should be between 1.75 to 2.25. But there's one more problem called multicollinearity. I wish I could have an econometrics course. I could explain all these things together. The multicollinearity problem basically in nutshell means that we want that there should be more correlation between independent variable with the dependent variable. We want it, yeah, but we don't want, listen carefully, but we don't want that there should be too much of correlation among the independent variable with one another. We want high correlation between the x variables and the y variable. We want high correlation between x1y, x2y, x3y, x4y, x5y. But just imagine the correlation between x1, x2, x3, x6, x7, x8 is massive. It means the independent variable, where is that graph? Let me show you because then it's easy to show. Where is the previous one? Yeah. So we want that the correlation between an independent variable and the dependent variable is high. That's what we expect. Yeah, it should be high. But what if, when we see the correlation matrix, the correlation between X1 and X2 is even higher? Then what happens? If your X1 and X2 are too correlated, then they can result some toxic impact on Y. Because if X1 and X2 are highly correlated, then why you have them both? Why don't you have one of them? So there's a double impact. So this double impact can affect your results negatively. Okay? This is called multi-collinearity. It's quite tongue twister. Yani, say it 10 times without stopping. Yeah, it's quite a tongue twister. Multi-collinearity. There's one more problem called heteroscedasticity, but I will not tell that. But anyways, multi-collinearity. And the question is, what are the legends? Where do we see that this is a problem or this is not a problem? Very simple, very simple. And by the way, both multi-collinearity and autocorrelation have the solutions. So don't worry that when you do your own analysis and you find that there is a problem, don't you worry, we can solve it. Okay, but what is the problem? Or is there any problem in the first place? If your VIF is 3 or above, it's a problem. If your VIF is 3 or above, it is a problem. But is it a problem? Huh? Is it a problem? None of them is a problem. All are below 3. In fact, none except one, that's only 2. All are below 2, actually. So nothing is touching 3. So as long as the value of value inflation factor is below 3, it's not a problem. So there is no problem. We don't have autocorrelation. We don't have the multicollinearity. Everything is good. But had there been a problem, we could have solved them. So these are your results, basically. Okay.
What if you, let's imagine that you would have one of those values over 3, what would you do? Just take it out, that variable?
Okay, just imagine that, I'm just writing it. I don't want to circle it. Let's say that this is 3 something. And this is also 3 something. And this is also 3 something. It means that instead of having one regression equation, we must have 3 regression equations. In one regression equation, we take this one, but we don't take these two there. So we keep them separate. So we run the regression 3 times. First time when we run the regression, we only have this variable and we don't have these other 2. And when we have second time run the regression, you take away from the activity box the first and third and keep second. And third time you keep away your first and second and keep third. You know, in your regression here, if you go back to the data, when you run the regression, here, and you see that you have your, like you enter the variables, you can also send them back. So if you have 3 variables which are causing this problem, take one at a time, then the problem would be eliminated. It's like there are 2 students in the class and they're always fighting. Okay, keep them separate, send them to one section and to the other one to another section. Hey, you be in the A section, you be in the B section. They never meet, they never fight. Life is peaceful. Same thing we do here. If there's too much of correlation between these 2 independent variables, don't keep them in same equation. Yeah, then it will not be a problem. So by doing so, we are able to get our regression outputs. This also I can save if you want, and I can share this output with you. Question is, do I have them? No. There's no need to save it. I think we can survive. But of course, you can watch the recording. That's everything for today.